All right, so guys, today we're going to talk about two other trends besides atomic radius. Okay, we're going to wind up talking about ionization energy. We'll also talk about electronegativity. So, ionization energy is simply the amount of energy that's required to take one electron away from an atom. So it's the amount of energy needed to make an atom into a single ion. And it'll always be a -1 ion as far as this is concerned for ionization energy. It will always. Most of the time when we talk about ionization energy, we're talking about the first ionization energy, which is the amount of energy that's necessary to take away that first valence electron. But there are other ionization energies. You can take 2 electrons away from an atom. You can take 3, you can take 4. So there are successive ionization energies. And it turns out that the successive ionization energies are always higher than the first ionization energy. So, and this is a little repetitious, but each successive ionization energy winds up being larger than the last. The reasoning for that, which isn't repetitious, is that when you remove a single electron from an atom, remember that the ion becomes smaller than the atom was. So that means that the remaining electrons that are attached to that smaller ion now are being held tighter because they're closer to the nucleus. They're closer to that nuclear force that's holding on to them. So that means that it's going to take even more energy to take away those outer electrons. Okay. And what we notice, I'll show you guys a chart in just a second that you won't have to copy, but is in your textbook. But there's a huge jump when core electrons are removed. When valence electrons are removed, there's a little bit more energy required, and a little bit more energy. As long as it's a valence electron, it's just a little bit more energy. But when you start removing core electrons from inner energy levels, that's when the atom really puts up a fight, because those electrons are really closer to the nucleus, significantly. All right. So, you guys graphed first ionization energy. Did you notice this? What happens? Here's the beginning of a period right here. Oops, let me get that pen. So here's the beginning of a period. Actually, that's the end of a period, sorry. Lithium is the beginning of the period. As we go across the period, what happens? It increases. Neon's the end of the period. Sodium's the beginning of a new period. As we go across sodium's period, in general, it's increasing. Is that rule perfect? Does it always increase from one element to the next? No. It's not absolutely perfect, but it is a trend. Okay, so it's a prediction that we can make. It isn't necessarily perfect, but it's a decent idea. Again, sodium to krypton, the noble gas. Rubidium, our alkali metal, to xenon, the noble gas. We're always trending up. Another thing that we can look at is, we were just talking about across. If we go up and down the periodic table, so if we go from the top of a group to the bottom of a group, like, say, for helium, to neon, to argon, so if we follow the noble gases down that group, what do you notice is happening to this trend here? It's always decreasing, right? Okay, so as I go down a group, it's decreasing. As I go across a period, it's increasing. Okay, and that's basically what this says right here. One more trend to go today, guys. And that'll be ionization energy, electronegativity, sorry. It's shocking. All right. So electronegativity is the ability for an atom, when it forms a compound, to attract shared electrons to itself. Okay, so this isn't about one electron, it's about 2 electrons. And it's about 2 electrons that are being shared. So we're dealing with covalent bonds not ionic bonds, because in ionic bonds they get lost or they get gained. Covalent bonds, they get shared. Okay. Sometimes the sharing is even, like in the case of chlorine and chlorine. Chlorine and chlorine will share a single pair of electrons in between them, and that sharing tends to be fairly even because one chlorine and the other chlorine pull similarly. They have the same electronegativity. Okay. Chlorine and hydrogen, however, have different electronegativities. Chlorine is a much better sharer than hydrogen. It's stronger. So it turns out that when the electrons are being shared between hydrogen and chlorine, they tend to spend more time with chlorine than they do with hydrogen. Like 60% of the time they're with chlorine and 40% of the time they're hydrogen. I'm not sure on those percentages actually, but that's the basic idea, is that more of the time they wind up with chlorine and less of the time they wind up with hydrogen. And the basic reasoning for that is that chlorine has the higher electronegativity. In fact, I can look this up. Chlorine has an electronegativity of 3.0. Hydrogen has 2.1 as far as its electronegativity is concerned. So that's why they wind up getting drawn closer to chlorine in this picture. Here's the basic gist for what you have to know for electronegativity. As you go down a column, it also will decrease. So an element's ability to share valence electrons decreases the larger it gets. And basically the reasoning for that is that the larger the atom, the less the pull the effective nuclear force winds up having. As I go across a row, though, atoms are getting smaller. So the electronegativity is going to increase as I go from left to right because the atoms are getting smaller. They're getting closer to that, closer to the nucleus, and the effective nuclear force is actually getting bigger as I go across a row.